Hi everyone, I'm Zahra Ronaghi, Engineering Manager at NVIDIA on the RAPIDS and AI Infrastructure team, and today I'll go through some of the fundamentals and core libraries of RAPIDS. So RAPIDS at a high level is an open source software suite of libraries that are designed to accelerate data science by running the entire pipeline on GPUs. It started at NVIDIA, but it's an open source project, so there's a lot of other groups that are contributing to the code as well. I'll talk about how we're trying to avoid extra copies or communication to host and how we're accelerating end-to-end workflows. What I'll do is I'll cover the building blocks of this framework or platform, mostly focused on data frame and machine learning, and then I'll briefly talk about our most recent library, cuSIM, for accelerating image I/O and in-dimensional image processing. Before we get into details of RAPIDS, here's also a couple of scientific use cases at NASA and NERSC that we've been working with. The video clip on the left is the GEOS composition forecast system that produces high-resolution 3D representations and distribution of chemical species in the Earth atmosphere in real time. So here we're looking at ozone concentrations, which is a pollutant that's harmful to both humans and the environment. So high concentrations are in white and low concentrations in dark blue. What we're doing is we're working with Christoph Keller, research scientist at NASA Goddard, on simulating chemical compositions of the atmosphere to monitor and better understand the impact of air pollution on the environment and human health. So specifically, we're exploring machine learning models since numerical models can be computationally expensive, and that can limit the ability to monitor and forecast air quality in real time. So throughout this collaboration, we've been porting machine learning models to GPUs with RAPIDS, and we were able to improve the performance by 50x, and as a result, provide forecasts in advance to help government agencies make decisions accordingly. And then on the right, it's an image of Perlmutter, the next supercomputer at NERSC, that will include over 6,000 A100 GPUs. We've worked with them to support a couple of scientific use cases. For example, one of these projects is working on understanding how applications at NERSC utilize the interconnect on the current cluster and how adaptive routing can influence performance. So we were able to port part of this workflow to GPUs with RAPIDS with 190x performance improvement compared to the original code on CPUs. I've also linked both blogs here if you're interested to read more about these collaborations. Okay, so looking at the data processing evolution, we've been using Hadoop for handling large distributed files, but one of the downsides is you'd have to read from HDFS, run some processing, and write the result of each part back to HDFS. So each stage of the job, you'd have two I/O barriers. And so along came Spark, which tries to hold everything in memory to eliminate these I/O barriers. You end up with faster processing since it's reading straight from memory instead of HDFS at each stage, and will end up in reduction of total runtime. But we can also do better and process some of these libraries on the GPU. Basically, we needed something to accelerate how we process data and do traditional machine learning. And so we've been working on accelerating pipelines and computation on GPUs, but we were still spending some time on read and write to host or CPU memory. Let's look at what initially was happening. Let's say we have two applications, one for machine learning and another for image processing. Both use GPUs today and offer great acceleration. After data gets loaded to GPU and after processing, we had to copy back to host memory, and we'd have to change formats on the CPU, and again copy that data back to GPU for application B. So traditional analytics would have to copy and convert data formats because they couldn't directly communicate on the GPU, and that caused too much back and forth movement. But what if we could keep our data on the GPU and eliminate this communication overhead? When data is loaded on the GPU, app A and B, for example, should be able to communicate and pass data around. We should be able to leave data on the GPU and concatenate a bunch of operations together to remove too much movement. And as a result, accelerate the whole pipeline end to end. And so removing these copy and converts actually is what led us to Apache Arrow. So very briefly, Apache Arrow is a language and hardware agnostic columnar data structure, and it allows us to do interesting things on the CPU without serializing and deserializing data. For RAPIDS, we also wanted to implement a mostly arrow-based memory model on the GPU as well. And the great thing is that other applications that can read and support the arrow format can read directly from pointers on device rather than copying data back and forth. So for example, if you're using the RAPIDS libraries and PyTorch, you'd be able to pass data without an extra copy back to CPU. So where we see this data process evolution going is not just eliminating I/O bottlenecks and PCIe bottlenecks, but also eliminating bottlenecks of serialization and deserialization between different libraries. So overall, depending on data and algorithms, we've seen up to 50 and 100x improvement depending on the application and data, which I'll talk about and show a couple of benchmarks. But basically, if you have applications that are able to use common memory formats and pass references back and forth between APIs, you can get huge performance improvements. And if we look at the traditional PyData ecosystem, it looks like this. We can use pandas for data cleansing, exploration, and analytics, scikit-learn for machine learning, NetworkX for graph analytics, and you can scale a couple of these libraries with Dask on multiple cores and multiple CPU nodes. And this is the RAPIDS software stack. Like I mentioned earlier, we built RAPIDS on top of Apache Arrow because it's a bridge between all of the different traditional big data and this new GPU accelerated platform. And we have three core libraries, cuDF and cuIO, which are our analytics libraries. Similar to pandas, if you compare the two charts, the API is also very similar. cuML for machine learning, which is similar to scikit-learn, and then cuGraph for graph analytics. We use Dask, similarly to the previous chart, to scale up and scale out on multiple GPUs and multiple nodes. And the best part is you can use these libraries in Python and not have to worry about writing CUDA C++ code. Here's a benchmark with cuDF and XGBoost, which was the first model that we released as part of RAPIDS. This is a mortgage workflow from Fannie Mae. Every month, they put out a file that contains mortgage that was given, debt-to-income ratio of customers, where they live, how well they paid previous mortgages. And so what we did was we loaded 200 gigabytes of this data, used XGBoost to train, and then ran a predictor on other mortgages that we didn't have information about. The top of the charts for CPU was done in Spark, and then we ran RAPIDS on a DGX2, which has 16 Volta or V100 GPUs, and also 5 DGX1s, which is 40 V100 GPUs. And these were hooked together with InfiniBand. So it took about 3 minutes to train on a DGX2, and the same workflow ran in about half an hour on 100 CPU nodes. So in general, everything ran in about 200 seconds. We were able to load data, prepare the data set, train and predict outcomes faster than we could even get the data ready and loaded on the CPU. And this shows RAPIDS improvement and optimization over time. So other than adding functionalities and algorithms, we still improve and profile and figure out where else we can accelerate and improve on. So this shows RAPIDS .2 compared to .10 and 17 release, where we added support for A100 GPUs, and the current latest release today is .19. All right, now looking at a couple of these libraries in more detail, cuDF is our data frame library that accelerates loading, filtering, and manipulation of data. If you're accustomed to importing libraries like pandas, this is pretty much the same, then calling functions that, again, are very similar. So it has a pandas-like API. And looking at the software stack on the right, CUDA C++ level library is called libcudf that you can use directly. And then the Python binding is cuDF, which interfaces to C++ and mimics the Pandas API. Anywhere that it doesn't, we're working on it. And then cuIO, which is part of cuDF, we have reader and writers for different file formats like CSV, org, Parquet. This will also support all types of decompression. For example, if you have a CSV file and it's gzipped or BZ2 or other format, you can directly load that onto the GPU, decompress, and start ETL right away. And then at the top, you see DAS QDF, which is used to distribute larger data sets across multiple nodes and GPUs. Like I mentioned earlier, the goal is to be able to import a GPU library, for example, in this case, cuML, and run machine learning algorithms on GPUs without writing CUDA code. Of course, sometimes it's just as easy as changing the import, and sometimes it requires changing few parameters and keywords. And that's our final goal, to leverage existing code instead of replacing it all. So the vision of cuML is a GPU accelerated version of scikit-learn. The API is also very similar, and it can also use cuDF data frames as input. This is what the software stack looks like on the right. The top layer that's exposed to the user is Python. Underneath that, Python wrapping C and C++, and connects C++ to Python. Our core algorithms are built in a combination of existing CUDA libraries, for example, Thrust, cuSparse, cuSolver, and machine learning primitives. What these machine learning primitives are, these are building blocks of basic operations that make the bulk of machine learning, like core, linear algebra, distance functions, matrix multiply, norms, transpose, and we're working on wrapping these primitives in Python as well. So for researchers that are working on new techniques and algorithms that aren't on our roadmap, what they can do is they can use all of these blocks without, again, having to write CUDA code. So they can put these blocks together and compose them into new models and algorithms that they need. And of course, all of this, again, connects down to CUDA, and we use Dask for distributing training across nodes or GPUs. And for example, here's a CPU-based clustering using pandas and scikit-learn, and then porting the code to GPU with cuDF and cuML. So in this case, just an import change, which is very common with a lot of the core algorithms, but sometimes you might see a deviation in some of the examples that we might not fully support yet, or sometimes additional parameters for how much GPU memory to use and things like that. But usually they're very similar. And here's cuSIM that I mentioned earlier, our latest RAPIDS library for GPU-accelerated in-dimensional image processing and image I/O. In this case, the API is similar to scikit-image and have mostly been implemented using CuPy, which is a GPU-accelerated implementation of NumPy, and it also includes some SciPy functionalities like FFTs and SciPy in the image. And so as a result, we're also upstreaming some of this work back to CuPy. And here's a benchmark comparing performance of some of the image processing algorithms, including registration and segmentation. There's also additional detail and benchmarks of lower level operations like filtering, color conversions, and labeling connected components in the blog that I've added below in case you're interested. Finally, another thing we've been working on and aiming for is interoperability. We don't want to reinvent the wheel. We're working on mimicking existing APIs and don't want to replace existing libraries, but we're more focused on complementing these. For example, a deep learning focused workflow in PyTorch, if we want to use cuDF for pre-processing, we can use CUDA array interface to go between these libraries without extra copies. So CUDA array interface is a standard format to describe a GPU array and allow it for sharing between different libraries without copying or converting data. So just like you can work with NumPy and pandas in the same workflow, you can now use cuDF and CuPy together while keeping the data entirely on the GPU. And so briefly, how you can access the software and get started. The RAPIDS container is available on NGC, which is NVIDIA's container repository, as well as Docker Hub. For bare metal installs, RAPIDS is also available through Conda, and it's usually the easiest way to install onto your machine. We also release nightly builds, so if you want to work on the latest development branch, that's also available. And if you're interested, you can download all this code from GitHub and build everything from source. Here's an example of the interactive installation guide. So if you go to the website, which is rapids.ai, you can choose the method, release, packages that you want to install, and you'll be able to just copy the command at the bottom, paste it into your workstation or terminal, and then install the libraries that you'd want to work with. There's also the GitHub link. You can access the repositories for these libraries as well as some additional ones like cuSignal, cuSpatial, and there's also a lot of notebook examples to get started. And then finally, feel free to join our Slack channel or add any issues, PRs, feature requests on GitHub. Thanks, everyone.